Hi, ladies and gentlemen. Welcome to our next lesson. We're going to talk about diagonalization today and an application for eigenvalues and eigenvectors. And really, we're going to take a look at Grant Sanderson's video where he talks about change of basis. This is a little bit of a difficult conceptual idea. And so what we want to do is make sure that we see it from a few different perspectives and see it multiple times in order to really understand what's happening. It's an extremely important idea which will carry through for the latter part of our course. So first things first, we're talking about diagonalization, and all of this is built upon eigenvalues and eigenvectors. And I will explain what that representation there is in just a minute. But it's really just all of the equations that generate from doing the eigenvalues and the eigenvectors. Talk about diagonalization. This is the whole concept of diagonalization right here. And then a go back really to what Strang introduced briefly in 6.1, which is the concept of what happens when we apply the same linear transformation repeatedly. So just like we did in the map program where we were recursively applying the linear transformation A, we're going to take a look at how we can do that more easily using eigenvalues and eigenvectors. Then some important results here. As long as the eigenvalues are not repeated, then we know the matrix can be diagonalized. If, however, we have repeated eigenvalues, then we don't know. We have to actually do a little more investigation, and it comes down to the set of eigenvectors. We'll talk more about that in just a minute. And the last topic we're going to talk about is similar matrices, which really, again, is back to the whole concept of change of basis. So we're going to leave you to read through this introductory part here. Just going to provide you with an explanation as to what Strang is talking about when he uses this representation here. So it's straightforward. All he's doing here is just saying that the matrix X is the matrix defined by the eigenvectors of A. So for example, let's say we have a 3 by 3 matrix, then X is just this set of eigenvectors. And what does this really mean? And of course, I have this written backwards. Sorry, I had to adjust here. I have this written backwards, which is actually important because the alternative is not true. So we may think as we're going through this that perhaps we could write this as lambda times x, but it turns out that that is incorrect, and I'll show you why that is. So what we have, going back and thinking about the definition of eigenvalues and eigenvectors, we have for every eigenvector, we have its associated eigenvalue times the eigenvector. And all he's doing is taking these vectors because A times X is just another vector, and he's thinking about putting these together. So we have AX1, AX2, AX3, this kind of thing. And of course, that's going to be equal to lambda 1 x1, lambda 2 x2, lambda 3 x3. And he factors out left multiplication by A, which is perfectly reasonable. So this is going to become A multiplied times the matrix that contains the eigenvectors, which, as we just said, is what he's using the capital X for. That's going to be equal to, well, we'd like to do the same thing here, but we don't have the same eigenvalue. So we can't just factor out an eigenvalue. We have to think about how this is going to work. And it turns out that we can extract the same matrix, the matrix whose columns are the eigenvectors, if we right multiply by a diagonal matrix where the eigenvalues are the diagonal elements. And now we can see why it has to be X times lambda. This is a capital lambda, for those of you not familiar. It's the lowercase lambda is what we were using here. And so to match up with the eigenvalue notation, which is pretty universal, we have the capital lambda here for the matrix. So we need to do right multiplication because when we grab that lambda 1, 0, 0 vector and sweep it through the columns of the x, we want lambda 1 times x1. If we were to left multiply by that matrix, we would take the first row with lambda 1, 0, 0, and we would sweep through and we would pick off the top elements of each eigenvector, which is nothing. That's not relevant. So we can't have it in this order. We have to have x and then lambda. And so this representation, every time you see ax equals x times lambda, this is what we're talking about. The X matrix is the matrix of eigenvectors. The columns are the eigenvectors. And then in the same order as those eigenvectors, we have a diagonal matrix, lambda, that has eigenvalues on the entries. And that's what he's talking about here. So you can go ahead and review this material. He provides us with a good example, which we're going to actually reach back into here, which is this example here. He's gone and diagonalized the matrix 2, 4, 6 by using the X matrix, the matrix of eigenvectors. What we want to do is look at now what we can do with this, as long as X is invertible. And so this comes down to our big requirement for diagonalization. X inverse must exist, which means that the eigenvectors are linearly independent. We have to have a complete set of linearly independent eigenvectors. That's what's required in order for us to do diagonalization. Then we have two options. So from ax equals x lambda, we can left multiply by x inverse, which would give us x inverse a times x equals lambda. And that's the example that he did that I highlighted in cyan up there. Or we could right multiply by x inverse, which would give us a is equal to x lambda x inverse. And this is really the situation that we are more interested in, because that is the whole concept of change of basis. Although you'll see the way Grant Sanderson presents it, it's actually the other way. So he provides these two representations right here, and he talks about them, and he talks about the power of being able to do several multiplications by a. So think now of where we're talking about the recursion. We have a times some vector z, and then once we get that vector, we're going to multiply by a again. And once we get that vector, we're going to multiply by a again, just like we did with the map program. This is recursive application of the linear transformation a. And you can see in this simple case, we have a cubed times z. And his point is, if we've diagonalized a, we can do this easily. And near the end, I'll show you an example of this. But what he says is, hey, if we replace a, and I'm not going to write it out because he's done it here. If we replace a with this representation, then what we can do is we can take and apply a several times simply by understanding what the eigenvalues are. And of course, we have a couple of zeros that he hasn't included in his matrix here, saving on ink for all that printing. So this situation is one that we're interested in when we're talking about the recursion. So let's take a look at his remarks. The remarks here are an important part of everything, and there's not a lot of moving parts here until we get to the change of basis, but it's good to review and make sure, right? Remark number one is summarized here. If we have distinct eigenvalues, then we automatically have a set of linearly independent eigenvectors, and that's what we need for diagonalization. We have to have linearly independent eigenvectors. That's remark number one. Remark number two is, remember that there's nothing magical about the order of the eigenvalues and the eigenvectors. When we wrote down ax equals x lambda, we could have defined x differently. We could have said that x is equal to the x2 eigenvector, the x3 eigenvector, and then the x1 eigenvector. There is no specific order for the eigenvectors. We can swap them around. So the diagonalization is not unique. The only thing we have to make sure of is when we do this, of course, lambda has to match up. We would have to put the second eigenvalue and then the third eigenvalue and then the first eigenvalue on the diagonal. And of course, all these other entries are 0. So what he does is he walks through and he shows us, hey, if I reverse the eigenvectors in the previous example, I end up with a different diagonalization of A. So you can compare the two cyan highlights that I have there. It's the same matrix. He's just changed the order of the eigenvectors to make this point that he's generating in remark 3. So because repetition is a good thing, remark 4 says, hey, not all matrices are diagonalizable. How do we have a situation where matrices are not diagonalizable? Right? Some of the matrices are going to have repeated eigenvalues. In the case where we have repeated eigenvalues, then we don't know whether we can diagonalize or not. We have to see if we have a set of linearly independent eigenvectors. So I have an example here. We're just going to take this matrix A, and immediately we can see, we know where the eigenvalues are. For any triangular matrix, the eigenvalues are on the main diagonal. So in this case, the eigenvalue is 2, and it's repeated 3 times. So let's find the eigenvector. That was step 1, which was really easy. There was no determinant to solve or anything like that. So step 2, remember, we're doing a minus 2 times I, and we're going to find the x vectors that satisfy the null space of a minus 2I. Calculating a minus 2I is pretty easy. I'm going to subtract 2 off of the diagonal, and that's going to give me 0, 1, 1, 0, 0, 1, and a row of all zeros. And the question we have is, what vector or vectors x is going to solve this particular situation? Well, let's take a look. What must be true about x? The last equation is going to be satisfied no matter what x I pick, right? Because I'm multiplying by this row of zeros. So when I multiply by the row of zeros, of course I'm going to get 0. What about the next row up? In order for me to have an x that I can multiply, the last entry is going to have to be 0. It doesn't matter what the first 2 entries are, but the last entry has to be 0 or else I can't satisfy the equation. What about the top equation? The top equation says that the second and third entries have to be negatives of one another. But we've already determined that the third entry is 0, which means the second entry has to be 0. And so what this leaves us is just one degree of freedom. We have just one eigenvector, and we can put any number we want up here. I'm just going to put a 1. But this is the only eigenvector we have. We don't have a second or third eigenvector. So we have 3 eigenvalues that are repeated, but we don't have 3 linearly independent eigenvectors. And as a result, the matrix A in this situation is not diagonalizable. It is reduced, if you will, as far as it can go. Let me just show you another example to make this point. The other example I want to show you is A is equal to 2, 0, 1, 0, 2, 0, and 0, 0, 2. Still, all the eigenvalues are 2. Lambda is equal to 2 and 2 and 2. The eigenvectors, again, I'm going to take a minus lambda I, which is going to give me 0, 0, 1, 0, 0, 0, 0, 0, 0, and try to solve for x. And in this case, we see that the only requirement for x, I need an equal sign there, the only requirement for x is that the last entry has to be 0 based upon the first equation. So I can have whatever entries I want for the first and second, which means I can build 2 linearly independent vectors. I can have an x1 that looks like this, and I can have an x2 that looks like 0, 1, 0. Both of those vectors are going to be eigenvectors. In this case, and we haven't seen this yet, we have a 2-dimensional eigenspace. So it's not just one vector and its scalar multiples. It's not a single one-dimensional invariant subspace. I now have a two-dimensional invariant subspace. Any linear combination of the two eigenvectors that I found will also be an eigenvector. This is what happens when I have repeated eigenvalues. We have the opportunity for a different type of situation than what we've been talking about. This matrix is also not diagonalizable because I didn't find a third linearly independent eigenvector. So these are just a couple of examples. Right? This matrix is non-diagonalizable, and this matrix is non-diagonalizable. Nothing we can do about that. He goes in and again repeats his remark from before, but he really doubles down on it. This is very important. Invertibility of a matrix is concerned with eigenvalues. Invertibility has to do with the eigenvalues. Remember, if we have lambda equals 0, that means the determinant is going to be equal to 0. And if the determinant's equal to 0, the matrix is singular. So singularity and invertibility have to do with the eigenvalues. By contrast, diagonalizability has to do with the eigenvectors. We need to be able to come up with a linearly independent set of eigenvectors. In the case where we cannot, our matrix is not diagonalizable. He provides a proof for this, but it's worthwhile just to go through. You don't need to read the proof. Just read through his result here and then this conversation. Really then what we want to do is emphasize the whole concept of change of basis, which again is in Grant Sanderson's video number 13. This is a video you're going to watch 2, maybe 3, maybe 4 times because it's not straightforward necessarily what we're doing. The concept, however, is not overly difficult once we start to think about it. What we're interested in is we are interested in the matrix A written as x lambda x inverse. So we have a matrix that we assume is diagonalizable. Remember, for every matrix A, there is a linear operator, a linear function, where given any vector x that gets put into that, it's the same as multiplying by A. Well, but if that's true, that's the same as x lambda x inverse multiplied by x. And the question is, what is this? Specifically, what is that? Let's go back. X is the set of eigenvectors. In fact, it's the eigenvectors, if they're linearly independent, form a basis for Rn. So the eigenvectors are a basis for Rn. What the matrix X represents is the change of basis for going from the standard basis to the eigenvector basis. That's what we want to do. We want to change from our typical basis, which is always the standard basis, ijk or e1, e2, e3, however many dimensions we have in our vector space. We're looking for a change of basis. So X contains the eigenvectors, which are the new basis vectors written in the standard basis. Relate this back to Sanderson's video. Okay? So this is the new set of basis vectors written in the standard basis. In order for us to transform from the standard basis into the eigenvector basis, we multiply by x inverse. So this seems backwards, but in fact, this is the way we're going to do it. So x inverse multiplied times the x vector, and I apologize, we have a lot of x vectors going around here. I probably should have, and I will actually. I'm going to change all of these vectors to z's. So we don't want to confuse things with the eigenvectors. So x inverse times z is the representation of z in the eigenvector basis. That's what applying the inverse matrix is doing for us. It's transforming us from the standard basis to the eigenvector basis. So now This is in the eigenvector basis. It is the vector z still, but we have changed from standard basis to eigenvector basis. Then what we're going to do is we're going to apply lambda. Lambda contains the action. It contains the essence of what the linear operator A is. We are now in the eigenvector basis, so applying that action is multiplying by a diagonal matrix, which isn't even matrix vector multiplication. We're just multiplying by constants. So we have this action. Once we get done with this step, we have applied the action of A to our vector z, but we've done it in the eigenvector basis. And so what we need is we need to transition back from the eigenvector basis to the standard basis. And that's what our last operation here is doing. This last multiplication by x is taking our vector z, which we have done the action of A on, and bringing it back into the standard basis. So this is really a three-step process, right? We transform, so this is z written in the eigenvector basis, and then we're going to apply the action of A to the vector z, but we're going to do that in the eigenvector basis. So this is applying A. It just doesn't look like it because we're doing it in a different basis. And then finally, we're going to transform back into the standard basis. So now we're back to the standard basis. This is the whole concept of change of basis. The piece that is really the challenging piece is to understand when we write the vector x, which is the set of the other basis, in this case the eigenvector basis, written in the standard basis, that when we multiply, we're really multiplying, when we multiply by that matrix, we're multiplying a vector that is in the eigenvector basis and bringing it back to the standard basis. So we need the inverse of that in order to do the opposite effect, to take a basis vector that's in this, or a vector in the standard basis, and put it in the eigenvector basis. That's really the more challenging piece of all of this. So that's the whole conversation of change of basis, and it's the reason that we're interested in being able to do the eigenvectors in the first place, is so that we can come up with higher and higher applications of A, but instead of having to do several matrix multiplications, all we need to do is increase the power on our diagonal matrix, which is very simple to do. And that's what he's talking about here. So, similar matrices. Matrices A and C are similar if the following is true. So the matrices A and C are similar matrices if A is equal to B times C times B inverse for all B vector or matrices that are, of course, invertible. I have to be able to find the inverse. And if you think about what this similarity means, it's just another conversation about change of basis. What it's saying is, if we take AZ, that's going to be the same as BCB inverse Z, but we already know what this means. This is taking Z from the standard basis into the basis that is the set of columns of B. So now we're in the B basis. Then we're going to apply the action in the matrix C, which is the same action as the matrix A. And the reason I know that's true is because once we've applied that action, we're going to transform back from the B basis to the standard basis, and we're going to have done the same thing that we would have done if we just multiplied by A. So A and C are similar matrices because they are performing the same action. And because this is true for any B matrix, it doesn't matter which basis we change into. We take our vector, we change into a different basis, we perform an action, and we transform back. And it's the same as applying a different matrix. Those two matrices are similar matrices. They're doing the same type of action. And he talks about this. He talks about how that relates to the eigenvalues, and you definitely want to read through and make sure that you understand similarity. Lastly, what he talks about is, and let me show you. So I have a MATLAB application here. Let me pull it up. All right, so what we have here is we have the standard basis vectors in green. So we just have X, Y, and Z, and this is just a three-dimensional image with the standard basis vectors in green. We also have a matrix, and it doesn't really matter. I can show you what the matrix is, but it doesn't really matter what that matrix is. It has a set of eigenvectors, and we see the black eigenvectors. So they have a couple of things about them. They certainly span R3. They're not linearly dependent vectors. They're linearly independent, and that's going to allow us to do a diagonalization. Also, we can see they're not orthogonal. The eigenvectors are actually not close to being orthogonal at all. And what we want to look at is we want to look at the red vector, which is our Z vector, that we are going to multiply times the matrix A. And the result of that is the blue vector that I have over here. So this is A times Z, and the input vector is the red vector Z. And what we want to do is look at how does this work in the other basis. So we know what it looks like in the standard basis, the green vectors. What we want to do is we want to consider what does this look like in the black basis. Well, the first thing we're going to do is take the input vector and we're going to write it out in the black basis. So written in the eigenvector basis, the red vector is represented by the magenta vectors. It's the decomposition of Z into the eigenvectors. And you'll notice these follow along. We have a couple of components here which are negative. They follow along the same invariant subspaces. All right, and then what we want to do then is once we have the components of Z, and you'll notice they're not projections. Because the eigenvectors are not orthogonal, we can't just use the unstated theorem that we talked about previously, where we just take dot products to find components. We actually have to solve a system of equations to come up with the magenta vectors, which are the components in the direction of the eigenvectors. Then what we're going to do is we're going to apply the eigenvalues to the magenta vectors. And when we do that, we end up with these changed magenta vectors. So let's go back. The dark purple here are the original vectors. So these are the original components for Z along the eigenvectors. And from this, we can tell what the eigenvalues are. This vector stays the same. It has an eigenvalue of 1. This vector doubles in length. That has an eigenvalue of 2. This vector ends up getting flipped around, and that means it has an eigenvalue of -1. So the eigenvalues for our matrix A are 1, 2, and -1, and they affect directly along the eigenvectors. So once we apply the eigenvalues to the darker purple vectors, we end up with what we found previously. And now those components are going to be the components of A times Z. That's what's going to give us the blue vector here. The blue vector is the sum of those three vectors. And so that's how we can use the eigenvector basis to map from the input to the output vector. And this may seem like it's laborious and like it's a waste of time, but there is a really important set of applications where changing the basis is important. In fact, this comes up much more frequently than we think. We're accustomed to using the standard basis, and that's wonderful, but oftentimes we want to change the basis into something else. For example, when I showed you the video of the flow, that was a change of basis situation. I didn't want to represent each of the images as just a list of pixel values. I wanted to change the basis into the eigenfunctions so that we could just use the most important eigenfunctions repeatedly to come up with a high quality approximation. We'll take a look at that application again. But that's exactly the same kind of thing as what we're doing here. All right. So the last thing that Strang has, that was our application, understand the change of basis. He talks about a specific example associated with Fibonacci numbers. And let me just briefly run through this. So we have a matrix 1101, which is actually, sorry, I wrote that wrong, 1110. And what this is doing is it's taking Fibonacci numbers and it is giving us the next Fibonacci number. So you know the Fibonacci sequence is 1, 1, 2, 3, 5, 8, right? The next number is just the sum of the previous number. That's easy to encode in a linear transformation. We are simply going to take the k value and the k minus 1 value, and we're going to multiply times this matrix, and that's going to give us the k value plus the k minus 1 value, and this is going to be the fk value. So we end up taking this value and shifting it down to the bottom of the vector, and then we end up building the next Fibonacci number, which is the sum of the previous two numbers. So this is a situation where we have recursion. We repeatedly apply the Fibonacci matrix over and over and over again to a vector. And in this case, Strang uses the vector u to represent the Fibonacci numbers, which is perfectly fine. So what he's done is he's called this f times the u vector at level k is giving us the u vector at k plus 1. So we can use this as a means of finding Fibonacci numbers. And he goes through the example of what happens when we apply the first, and then we come up with our 1, 1, and then we come up with 2, 1, and then we come up with 3, 2. The next one's going to be 5, 3. The next one's going to be 8, 5. It just keeps finding the next number. And he says, hey, we can, using eigenvalues and eigenvectors, change the basis. So instead of thinking about the representation of the numbers in the standard basis, we can use the eigenvector basis, and we can find the eigenvalues. And we can come up with a formula to represent any Fibonacci number we want as a linear combination of the eigenvectors. So let me rewrite this in terms of, right? So he's really saying that we have lambda 1 raised to a particular power divided by lambda 1 minus lambda 2, and that's being multiplied times the first eigenvector. And then we have minus lambda 2 raised to the 100th power. This is to find the 100th Fibonacci number, divided by lambda 1 minus lambda 2 times x2. We have a linear combination of the two eigenvectors. And he gives us, it's easy to solve, of course. It's a 2 by 2 matrix. We can easily find the eigenvalues and the eigenvectors, but he gives us the representation, the exact representation for the eigenvalues in terms of irrational numbers. They include the square root of 5. Some of you may recognize the golden ratio. That's this number here. That's the golden ratio is 1 plus the square root of 5 divided by 2. That's one of our eigenvalues. And the other one is 1 minus the square root of 5 divided by 2. And we can come up with multiples of these eigenvalues multiplied times the eigenvectors. And he lists the eigenvectors for us right here. That's the first eigenvector, and that's the second eigenvector. And we can generate the, without having to do matrix multiplication, the Fibonacci numbers. So we can easily find these values without having to do all of the matrix multiplication. All right, so the recursive powers of K, here's the matrix A that I showed you. You can play around if you want with this. The eigenvalues, remember there was a 2, there's a 1, and there's a negative 1. And so, and I can number these, that's fine, 1, 2, 3, but then you know what's happening. You can find the eigenvectors. This is an easy thing to type into MATLAB and find the eigenvalues and eigenvectors. And you can understand that any vector that we feed in to end up multiplying A times Z, we can take that Z and rewrite it as a linear combination of the eigenvectors. And then using that linear combination of the eigenvectors and these scaling factors, we can figure out exactly what's happening for the output of A times Z. So because we can do that, and he walks through this, this is really just the Fibonacci conversation. It's really easy to apply the same matrix over and over and over again. All right, so that's the end of the conversation on diagonalization. We do have a little bit more in terms of an example here. Just a brief comment about non-diagonalizable matrices. I've already shown you a couple of examples. We are not talking about algebraic and geometric multiplicity. So this entire conversation down here is not part of what we're covering in this class. Review of the key ideas, and then again, worked examples. Recommend that you look through all of these as you're going through and learning the material. So the questions are right here, having to do with Grant Sanderson's video. You get a chance to practice with the Fibonacci numbers, and then this is the same matrix we had last time. You're just going to diagonalize this matrix. If you need a refresher on the inverse of a 2x2 matrix, that's on page 50 in Strength's book. All right, thanks.